Bismillah ar-Rahman ar-Rahim. Welcome to lecture 5 on digital signal processing. عنوان هذه المحاضرة هي typical sequences and sequence representation. Okay, so typical sequences and sequence representation. Okay, so we'll start with some basic sequences. The very elementary basic sequence is the unit sample sequence. Or sometimes we call it the discrete time impulse, or simply we call it the unit impulse. The definition of the unit sample sequence is delta of n. So we use the same symbol as in the time domain, in the continuous time domain. So delta, instead of delta of t, we can define it as delta of n. And this is equals to 1 for n equals 0, and 0 for n not equal to 0. Graphically, this is represented with a stem of an amplitude of 1 at n equals 0, and all other values from the right side and the left side are all zeros. So this is the unit sample sequence. It has it has 1 amplitude of 1 at n equals 0 and 0 otherwise. Just to mention that we can have also shifted delta by k, and this one is also equals 1 for n equals k, and 0 for n not equals to k. Okay? If we take an example, you can say, or you can find that this is 1 at n equals 2, and 0. This is delta of n minus 2. So delta of n minus 2, it is 1 for n equals 2. So when the argument here inside is equal to 0, so this is equals to 1, otherwise it's equal to 0. When n equals 2, so it's delta of 2 minus 2, delta of 0 is equal to 1, otherwise it is equal to 0. So this is the unit sample sequence. Let's move a little bit further and define the unit step sequence. And again, we will use the symbol mu instead of u, mu of n, and mu of n is equal to 1 for n equals or equal n greater than or equal 0, and 0 for n less than 0. And the unit step is all ones starting from 0 and above. 0, 1, 2, 3, and all those values are ones and 0 in the left-hand side. Okay, so this is the unit step sequence, and a shifted unit step is also 1 for n greater than or equal k, and 0 for n less than k. So if you have a shifted version by a negative, so you'll have here -1, -2, and this one is mu of n plus 2. So when you have n equals to -2, -2 plus 2 is equal to 0, so your mu of 0 is equal to 1. Whenever is the argument inside the brackets is greater than or equal to 0, this mu of this argument is 1. Otherwise, it is equal to 0. Okay? Okay, one representation of mu of n in terms of the delta is to have these are train of deltas. So this delta is at 0, this delta is at 1, and so on. So we can say that mu of n is equal to delta shifted of n minus m from m equals 0 up to infinity. And we can also represent mu in terms of delta in the following equation. This is from k equals minus infinity to n delta of k. Okay, this one here needs, just think about it a little bit and see what will happen. This is our maximum of the index. The maximum of the index is n, where n is the argument here. So take an example for n equals -2. It's equal to the summation from k equals minus infinity up to -2 delta of k, and all those should equal to 0. If you take m of 3, for example, then you have a summation from k equals minus infinity up to 3 delta of k, and this one will include all the values of delta inside here, k, from minus infinity to 3. As long as we pass through the 0, for k equals 0, it is here, then we have those values, delta of -1 plus delta of 0 plus delta of 1 plus delta of 2 plus delta of 3. Those are all zeros. And we have delta of 1. This one is equal to 1, so the answer is 1. So whenever you have a positive argument for n, you have 1. Whenever you have a negative argument for n, you have 0. So mu of n can be represented in this form here. Okay. How can we represent delta in terms of mu? So this is a representation of mu in terms of delta. So we have two representations. Delta of n can be represented as mu of n subtract from mu of n minus 1. Okay, think about this. Draw mu of n, draw mu of n minus 1, and subtract them from each other. If you draw mu of n, it is 1 starting from n equals 0. So this is n equals 0, 1, 2, 3, and so on. And those are zeros. This is mu of n. If you draw mu of n minus 1, it will start from, so this is n equals 0, 1, 2, 3. This is mu of n minus 1. So it's shifted by 1 to the right. If you subtract this one from this one, you end up with this sample only, which is the delta. So mu of n minus mu of n minus 1, mu of n minus mu of n minus 1 is equal to 1 sample at n equals 0, which is equal to delta of n. Okay, so these are the two basic samples. Let's go to the third one, and which is the sinusoidal and exponential sequences. The sinusoidal sequence x of n is equal to a cosine omega 0 n plus phi. This is for all n between minus infinity and infinity. So x of n is defined in this manner, where a, omega 0, and phi are real numbers. A is the amplitude, omega 0 is the frequency, and phi is the phase shift. Okay? We know this from previous courses in signals and systems and from circuits also. So A is the amplitude, omega 0 is the angular frequency, and here it is in radians per samples. It's not in radians per second. We will come to this later when we define the sampling process. In next lecture, we'll define the sampling process and we'll talk about it. And we will mention the difference between the angular frequency in discrete time and the angular frequency in the continuous time. Phi is the phase angle. The phase angle. Okay. The other part is the exponential sequence. Exponential sequence, x of n is equal to a alpha to the power n. It's also defined for n between minus infinity and infinity. Alpha here is equal to, in the general case, is equal to the e to the power sigma 0 plus j omega 0. And a is also a complex quantity. In the general case, the magnitude of a e to the j phi. If we combine those, then our x of n is equal to the magnitude of a e to the j phi times e to the sigma 0 plus j omega 0 times n. X of n can be written as the real part and imaginary part. Let's put them in this form. A e to the j, sorry, the real part has no j, so this is e to the sigma 0 n. This is the real part times e to the j omega 0 n plus phi. Have the real part to be a e to the sigma 0 n cosine omega 0 n plus phi plus j, this is the magnitude of a, and here also the magnitude of a e to the sigma 0 n sine omega 0 n plus phi. This is the imaginary part of x of n, and this is the real part of x of n. The real part of x of n. Okay. This, the the sinusoidal and the exponential, they have the possibility to be periodic. So we'll check the condition for periodicity of sinusoidal sequences. Okay. Let's take x1 of n to be a cosine omega 0 n plus phi, and we need to check for periodicity. Is this function, is this sequence periodic or not? Okay. For periodicity, this function has to comply with the periodicity condition, which means that we have to apply if x1 of n equals to x of n plus capital N, that there is a certain n such that this function will repeat itself. This is for all n between 0 minus infinity and infinity. If this is true, this means that we have a periodical function. So if we let x2 of n equals to x1 of n plus capital N, and see what will happen. So this one will be a cosine omega 0 n plus capital N plus phi. So this is our x2 of n. Okay, expand those, the argument inside. So this is a cosine omega 0 n plus phi plus omega 0 capital N. So we'll take those as one angle, and this one is another angle. So this is the cosine of the summation of two angles, and this is equals to a cosine omega 0 n plus phi cosine omega 0 n capital N minus sine omega 0 n plus phi sine omega 0 capital N, and we close the brackets. Okay? If we have to check for periodicity, this function is periodic if x2 equals to x1. If x2 equals to x1, then we have a periodical function, okay? Which is what we have here. So for this one to be a cosine omega 0 n plus phi, this one here, this item should be 1, and this item here should be 0. So we need to find which angle. So the two conditions, so we need cosine omega 0 n equals 1 and sine omega 0 n equals 0. For those two conditions to be satisfied, it means that we have to have omega 0 n is equal a multiple or integer multiples of 2 pi. 2 pi times r, which is integer multiples of 2 pi. Put it in a nice form to be 2 pi over omega 0, the ratio of those two is equal to n over r. N over R is an integer over an integer, and we call this as a rational number. So our check for periodicity of any discrete time sequence, sinusoidal discrete time sequence, is to have the ratio of 2 pi over omega 0. If this ratio is a rational number, then we have a periodical sequence. Otherwise, it is aperiodic. Okay, let's take an example. If we have xa of n equals cosine 0.45 pi n, and let's take xb of n equals to cosine 3.14 n. Okay, for the first one, we have omega a, which is equal to 0.45 pi. So the ratio of 2 pi divided by 0.45 pi, so we cancel pi with pi, so this is 200 over 45, which is equal to 40 over 9. So 40 over 9 is rational number, and this one is periodic. Not only it's periodic, so we have to manipulate this ratio until we have no common factor to be manipulated, and we can say that NF is also equals to 40. We cannot say that this 200 over 45, 200 is also N, but it is not NF, it's not the fundamental period. The fundamental period, to find the fundamental period, you have to manipulate the figures and see the numbers such that there is no common factor that can be cancelled from the numerator and the denominator. So 200 divided by 5, it's 40, divided by 5, it's 9. No common factors here, so NF is 40. Okay? NF is equal to 40. Okay, for B, so we have omega B equals to 3.14, and 2 pi over omega B is equal to 200 pi divided by 314, which is equal to 100 pi divided by 157. So this is irrational because it contains pi, irrational number, and the function xb is aperiodic. Okay? Okay. Okay, the last item in this session will be talking about the general representation of any arbitrary sequence. So let's talk about it. Representation of an arbitrary sequence. Okay, let's take an example. We'll take a signal with 0.5 at -2, 0, -1, 0 at 0, 1.5, -1, 1, 0, 1, 2, 3, 4, 1, sorry, 0, 1, 2, 3, 4, 5, 6, and all other values are zeros, and here all other values below this one is all zeros. Okay, so this is an arbitrary sequence. I'm going to represent this in terms of shifted deltas. So I'm going to say that x of n is equal to this 0.5 here. Everything here is 0. Above 6 is 0. So below minus 2 is equal to 0. So this is equals to weighted delta. The weight is 0.5 multiplied by a delta present at n equals minus 2. So this is delta of n plus 2 plus 1.5 delta of n minus 1 minus, we have a minus 1 at 2, so it's minus 1 delta of n minus 2 plus, we have 1 at 4, so 1 times delta of n minus 4, and the last one is 0.75 delta of n minus 6. You can see that any arbitrary sequence can be represented as weighted deltas shifted at the corresponding or the appropriate index. So x of n are summation of weighted deltas in this manner. So if you have any sequence, you can put it in this manner, and we can generally say that x of n is equal to summation, giving that using this representation. Notice that this one here is x at minus 2. This one here is x at 1, x at 4, here x at 2, and here x at 6. So we can say x of n is equal to x of k times delta of n minus k, for k equals minus infinity to infinity. Some of those x of k's are zeros, like here. Some of them are non-zero values as those values, but in general, x of n can be put as weighted shifted deltas from k equals minus infinity to infinity. Please keep this in mind. We will use it later on when we talk about when we start talking about systems. Okay? Okay, thank you very much, and I hope you will enjoy this lecture, and we'll see you in next one.